Thank you.
Thank you very much, Maria, for the kind introduction. Thanks to all of you who have tuned in for the second day of these talks and then fourth day in this series. So yesterday we spoke a little bit about the dangers that come from automation, indiscriminate data vacuuming, and maybe the less brainy types of approaches to data analysis and to generally, treating our data, right, or processing our data. Today, we will try to talk a little bit about confronting maybe slightly more brainy data vacuums. So we're talking about processing schemes which are a little bit more elaborate than just basic statistics. So here we refer more to machine learning, of course, other types of artificial intelligence, and we'll be talking a little bit about profiling, automated decision-making, explainable AI, and so on and so on. So today we might spend a little bit longer than yesterday, so it might run very slightly over time, but I hope that it will be interesting enough to stay with us. So yesterday, just as a taster, we spoke of this case where AI went wrong for a company that was basically building a whole division and a whole vertical around data processing and analysis. So this is the case of Zillow, where multiple millions of dollars basically were wasted because their algorithm that was learning how to trade real estate was not exactly as good as they expected, right? And it didn't predict certain things that happened in the market. So the median error rate was supposed to be quite low, but it turned out that it was 3 times the rate that they expected, more than 3 times the rate expected for, let's say, non-traditional cases, which made it into a big problem. And then, the amount of trades that this algorithm was able to make properly was diminishing over time. The consequence was that 2,000 people, which were 25% of the company's workforce, were fired. And that is purely because of an algorithmic mishap, right? So in a way, you could say that this had an important effect on their lives, purely because of an algorithmic question. I think the write-off they had was in the order of 300 million. So when it says millions, it in reality is hundreds of millions, right? So this means a lot of money was lost. Then another case, which is very important, I think, to keep in mind, we'll come back to that a little bit later as well, is that machine learning models often memorize to some extent the training data that we put inside them. So here is an example from maybe 4 or 5 years back, where you would be able to put some repeated text or repeated characters into Google Translate, and then it was like a spell, right? It would trigger Google Translate to produce a completely unrelated text, that mixes, the end of the world with the Bible and some other things, right? In a very short, paragraph, the size of a tweet. So obviously, there's things hiding there that we might or might not be able to unlock, and it all depends on the complexity of the models, if we can explain them, and so on. And we'll come back to that a little bit later. So that's another risk that comes, with machine learning. And, big players are today very acutely aware of that because they have methods and algorithms to minimize this kind of effect. So they have ways of trying to minimize this memory effect and ensuring that it is not too difficult. But as you can see here, these things happen. And then this is only one of many examples that they found at the time. Then all of you have heard of deepfakes. It's a combination of deep learning and fakes. It's a mishmash of 2 words. And deepfakes basically are constructions, which are visual constructions, which let you put the face of somebody else on a body existing in a video or in a picture. So here you see, I would say, almost a work of art from a YouTuber called Control Shift Face, who specializes in making deepfakes based on the ideas of users. And this is Kevin from Home Alone, so I think the season is almost right, except the face is that of Sylvester Stallone. So it's, it's almost creepy, right? Like this is a very famous scene. He's watching TV, and you see Sylvester Stallone's face, staring at you with that hard stare. So, it's funny, but at the same time, it's scary because that could be, your face, or that could be your body and somebody else's face, right? And what do we do in that context? So it's an issue from the point of view of privacy, and it's an issue from the point of view of security. Someone can put words in your mouth. You've probably seen that video of Jordan Peele, speaking like Barack Obama, but to a video that's a fake video of Barack Obama, right? And so again, it was a video that was meant to highlight how easy it is to do something like that. The other reason why it's important is because this technology is, very easily usable. So it's very easily put to a bad use. And today, if you look, for example, at companies that do face identification, whether it's 2D face identification or 3D face scanning, which is kind of the more recent thing, there's a very well-known class of attacks which are called morphing attacks. So you would take, for example, an identity document that you've stolen, and you don't put your picture inside, but you put a picture that is some kind of average between your picture and the picture of the person who's in the passport, right? So even if those who are checking the passport, if the verifiers are looking at the picture, the original picture of that person who's supposed to be in the passport from somewhere else, they see, something that resembles what is out there, right? And what is out there is a mix of your face and the face of that person that you've kind of digitally composed. So these kind of morphing attacks are very challenging to discover and to avoid as well. So you can fool many very well-known identification systems using those attacks. And then there's also other fakes. So they can be, for example, visual fakes. So you can generate audio that sounds like somebody specific, right? Like a specific person that you would be able to, you can basically impersonate somebody there. Then there's another aspect. For example, you could say, well, because that is possible and everybody knows that this is possible, then that video that shows someone taking a bribe is fake, right? That was not that person, that was somebody else, and that was just faked in order to, dirty the reputation of someone otherwise, upstanding. So the ability to do that, which is obviously already kind of out of the bag, opens up many questions that have to do with privacy and security. Face recognition is one of the main applications of AI that I would say are privacy challenging. Stephanie spoke about it a lot on the first and second day. But what I wanted to speak about is specifically how face recognition takes you to policing capabilities. So we might have mentioned this example yesterday where there was a person in China who was on the kind of wanted list by the local police. And that person was hiding for a long time, but then they decided to go to a concert with 60,000 other concert goers. And the police fished them out from that crowd of 60,000 people using purely facial recognition cameras. So facial recognition pinpointed that person who was on the list, the computer had a picture, and then said, okay, that's the guy, so pick him up. And there was a video, and it was a pretty big story because it demonstrates how mass and automated profiling and capture of data can find a citizen wanted for some kind of crime. So in China, I think already in 2019 or 2020, they estimated there were about 170 million face recognition cameras, and that number since most likely has grown. But this is not to single out China. This is just to say that that's a nation that's at the forefront. Western nations are doing the same thing. So if you go to London, there's cameras left and right. If you've watched this recent Netflix documentary about AI and facial recognition, then there's examples there of activists who are battling cameras kind of placed on corners, and if someone covers their face, they get arrested, and so on. So these things happen. There's sometimes innocent people who are captured through the system. The question, of course, is the error rate higher than it would be with a traditional method? Does this really help us as a society? And I think, depending on who you ask or which society you look at, some will agree and they will say, yes, that makes a lot of sense because we're a safer society now. Other societies will say, well, that doesn't make sense because we are feeling watched all the time and we cannot be truly free and exercise full human agency if we are watched all the time, right? It's the panopticon effect that we spoke about also in April. So, there's many questions around this kind of recognition. There was this story also of Clearview AI in the US, which was secretly composing databases of American citizens. And then they were selling that data to policing agencies and law enforcement. And that, the main problem with that was that it was happening behind the public's back, right? So people wouldn't know if their face is in a facial recognition database or not. And then, what kind of standard do you apply for facial recognition, first of all, right? So if we apply something automatically as a law, we should ensure that it is fair. But that is a big challenge. We don't know if that is fair because there is not a good standard for facial recognition. And, NIST, the American Institute for Standards, ran some fairness tests on some frameworks and found that they were between 10 and 100 times worse in one-on-one matching of African American and Asian faces, right? So again, this is this bias that goes into training. The algorithm will only be as good as the people who put in the data, right? So if researchers kind of, said amongst themselves, okay, we're going to take pictures from ourselves, we're going to agree to put it in a database, so they did so, and it so happened that they probably were, white and male and so on, then those are the pictures in the training database, right? And then you sell an algorithm, you test it on yourself as a researcher, most likely in good faith, right? I wouldn't blame them necessarily that they missed something big, but that's the way things normally go. And then you end up with an algorithm that is definitely not fit for public use, right? So there needs to be this conversation between, the representation that we have in research and whatever you can find on the other side and what the algorithm actually thinks that is happening. So there's a lot of interesting problems around this area. So, AI in policing goes well beyond faces. Face recognition is the first thing that is being applied. So, for example, in the US Capitol attack, which took place not that long ago, there was lots of video that emerged from that, right? You can see that even if you look at, the war in Ukraine, you see tons of videos emerging from both sides, right? Even in war, you see videos. So it's kind of become a part of our life that everything is filmed. And then the police and basically security agencies in the US took those videos and they applied facial recognition and then could find some of the perpetrators of that attack, which otherwise may not have been identifiable. And that's a proven case that this was used in that investigation. Then there are cases of, for example, crowd-funded crime reporting. There are apps where you can report crime or suspicions of crime in your neighborhood. And then, some kind of algorithm or model on the side of the server is going to try to extrapolate and see, where crime could be committed. And it leads to so-called predictive policing, where police patrols would be sent to neighborhoods where the app or the algorithm is saying there might be more crime. Again, I'm not debating whether that is the correct thing to do or not, but I want to highlight that this is obviously having an impact on the privacy of those who may be involved, on whatever end of this in this scheme. And we all know that not for everybody, a contact with the police has to be pleasant, right? It doesn't always work that way. And there are some groups of citizens which may be disadvantaged, right? In some cases, the algorithm might be right and might improve our ability to catch criminals and generate a safer society. But what I'm saying is that there's a certain price we're paying for that, and we should really keep an eye on that because it's not evident that it works the way that it is designed. Then there were some other cases, such as, for example, the US police were using a predictive algorithm to prioritize arrest warrants. So if the police have to arrest a bunch of people, they don't know who is the most likely to commit the crime next or who is the most dangerous one. And then the algorithm basically emits a recommendation. And based on that recommendation, they would then prioritize that list and then visit the places where they would think those who are wanted are hiding. In a way, this is also applied in the judicial system. So there are algorithms that basically predict the probability of reoffense that would come from certain defendants. So the judge would be seeing a defendant. They are let's say, a recidivist, which means they've already offended before. So then the algorithm would say, okay, the algorithm predicts that that's a probability of reoffense, and it's going to probably happen in this time scale. And based on that, the judge is going to emit a decision that's going to put the person in jail, maybe for 2 years, maybe for 5, or maybe for 7. So in a way, you are getting jail time that's based on a suggestion that's coming from a computer. And again, is that fair? Is it, justice is supposed to be infallible, not statistical. So maybe that's not the place to apply it. So we should also think about whether that's the right thing. Then, if we take it a notch further, we could think, okay, policing is meant to protect us, but then there's also something much worse, which is war, right? Nobody wants war. It's a bad occurrence. And I asked the AI, how does it see itself as a robot during war? And these are the images that I got back. So this one is, almost cute, like from War of the Worlds, kind of 50s style, okay, big robot with this kind of, strange, with this kind of strange light in the middle. It's almost like a mix of Metropolis and War of the Worlds, right? It's almost an aesthetically pleasing picture. But then I also got this, which is on the right-hand side, and this is just terrifying. I mean, at least to me, it is terrifying. It's some kind of, mobile platform on which there's something that looks humanoid, and I don't know if it's, destroying these buildings or doing something else, but that's definitely not an image I would want to, have in my head, right? So, and this is just an AI making pictures. It's really innocent, right? There's nothing else in it. So I would think that, there's a lot to explore in that domain. So in 2017 or 18, the RAND Corporation, which is a very esteemed research institution, wrote a report that is very long, it's about 200 pages, that explained what is the likely development of artificial intelligence in military applications. And basically they said that, first of all, there is a likely increase in military AI. The public in the US, because it was a report focused on the US and then their adversaries, the public supports continued investments, especially if the adversaries use autonomous weapons. So what this means is, if they are using AI and autonomous weapons, then we definitely should do the same thing, which basically, as you can see, escalates the situation, right? There's no likely ban on AI and military in the near term in any country. And then internationally, of course, there are other powers like China and Russia who are developing AI and are also successful in that domain, right? So what we're saying is that the world military powers are definitely looking at this and definitely developing in many different directions. And the report especially singled out China as seeing AI very clearly as a critical component of their strategy, especially when they would see themselves going against more technically advanced adversaries. They would then turn to algorithms or to automation and software in order to combat that. So there's been a lot of development in all these countries around autonomous robots, operational support robots. So these are physical devices usually that have some kind of autonomy. Stealth attack drones, UAV, so unmanned aerial vehicles, swarms, and so on, even autonomous targeting software. So you see that with the proliferation of this automation and software and then sensors as well, which are more and more precise and easier to get. There are phones, cell phones today with infrared cameras, which are very precise. You don't really have a lot of places to hide as a soldier in the trenches, right? So that truly generates many ethical questions around the nature of war and the way that war would be waged throughout the 21st century. I would hope that this is not our future, but unfortunately, the signs are pointing to these elements being definitely in our future, and that makes me very anxious. So to give you a few examples, research in AI and war goes very far back. In the 80s, the Americans had the Aegis program, which was basically a kind of sea-to-air type of defense primarily. And then this system could perform many functions autonomously. So it had several so-called doctrines. It could do semi-automatic operation, it had another automated mode, and it had a special automated mode. And then for some of these modes, it was so-called human in the loop. So it means that the human would have to take a decision and then make the system act, right? So even if the system autonomously targets and then can autonomously shoot down that target, the human would have to take an action. But then there were modes as well in that system that basically allowed an overwhelmed operator to delegate those decisions to the computer. And then the computer would entirely take decisions. The human would be not in the loop, but they would be on the loop. So they would simply be informed of what is happening, and then they can interrupt it. So it's a very big difference in terms of what's happening, right? And then you heard probably about Iran Air 655, which was shot down towards the end of the 80s, which was a human error, but it was, in connection with that system. So that's something to think about. Then Phalanx, this defense system that, shoots a lot of bullets at a target. You've probably seen some videos basically creating streaks in the sky. It was already a system that was relatively automated towards the end of the 70s. In an exercise in the 90s, it shot down a friendly plane. If I remember correctly, the pilot survived, but generally speaking, that was again a mistake that can occur. Then there's Patriot missiles that have shot down both planes in the US and in the UK, and there probably these were cases of so-called automation bias, where humans who are in the loop trust a little bit too much the system, and then they would rely a little bit too much on automation and get used to it. So again, this can happen. Then there's a few other projects which were quite interesting. So there's anti-radar missiles that can fly around and look for a target, and then they just go for it when they find it. There was the X-47B plane from DARPA that performed an autonomous landing on a carrier. If you've ever seen a landing on a carrier and you know how everything is moving, one tiny mistake can completely wreck the operation and then generate a lot of trouble, including destroying the plane. It's extremely difficult to do that. And nevertheless, they built a system which almost a decade ago managed to land this plane completely autonomously on the carrier. Then, these are not only physical devices that can kind of, move around and do something. Most of the time, there's not a lot of research going into devices that kill automatically, right? This is still a barrier that in some countries is considered, a pretty red line. So there's not much in that respect necessarily, but you can see that the capability is there, and sooner or later we are probably going to get there. But what I wanted to say is that this is not purely a question of physical robots. This is also a question of software. So, for instance, AI was used extensively in the DART planning tool that the American Army was using, for example, to deploy in Iraq in the 90s. And DARPA said that just that use of that tool single-handedly made a return on investment of 30 years in AI that was put in DARPA. So just that one use of that one system was enough to repay all the investment made in that tool. Then there's another tool they have, which is called SAPE, which was planning, basically planning deployments for a potential nuclear war. So the kind of planning that used to be done in 18 months, using this tool would be done only in 3 days. So basically, they could game lots of scenarios using this tool, right? So we are very, very close to something very dangerous, right? We are close to an automated tool telling real people where to go in the case of a nuclear attack, right? And that tool is deemed more efficient and faster than human planners would be. So again, it can have a very real impact on our life. And of course, by transition, our privacy, because if we are dead, then our privacy is dead with us, right? And that's the topic of discussion.
Or safe.
or we're eternally safe, but I would hope that it doesn't come to that. Okay, and then there's robots that get guns on them. This is a combination of a Ghost Robotics frame. I think they were called Ghost Robotics. I'm not sure. Yes, Ghost Robotics, and then a gun that is made on top, which is a kind of semi-autonomous rifle or an autonomous rifle. So you have an autonomous robot carrying an autonomous rifle. You can see where this is going, right? And this is a picture from, I think, last year. So this is very similar to what Boston Dynamics are producing as robots, but it's not a Boston Dynamics robot. And they actually say they prohibit military use of their robots. So they basically say our robots are not going to go that way, and they are quite opposed to what Ghost Robotics were doing, and that's a separate company, right? Just yesterday, I saw a piece of news that said that the San Francisco Police Department is now giving guns to robots. So I didn't read in detail, whether these robots would have autonomy or there's a human operator basically driving them. But that was the message, right? That this is happening. So you see how this is impacting our existence, right? So this is very scary stuff. It makes a lot of people anxious. It definitely makes me anxious. So how do we control this? Or, as a society, what can we do? And then, maybe we can tone it down a little bit, move away from war or from policing, because these are extremely difficult aspects also from the ethics side. But think, generally speaking, in terms of artificial intelligence, machine learning, sucking in a lot of data, learning a lot of things with algorithms that we don't always see, and sometimes even with the good faith of the makers of those algorithms, what do we do? Well, one option is self-regulation. So we could say, well, the entities that need to do that need to regulate themselves. And in some countries, this is the favored policy. I think this is a failed policy because, we've had this happen in many other domains, and it didn't really work out very well, right? Because the prerogative and the incentives that those companies have is very different from those that their users or their or the general public would have, right? So maximizing some corporation's profit is definitely not my life goal, but protecting my privacy is. So you see there is a mismatch of incentives. So we have to keep that in mind, right? So basically, applying kind of free market principles, I think doesn't work in that case. Another case is regulation or the so-called law. I think this is a very strong lever that we have. I think it's very important to lobby our lawmakers, whether they are local lawmakers in your countries, whether they are lawmakers in the European Union. So for those of you who are EU citizens or here in Switzerland, it's very important to keep an eye on the ball and to keep pushing. Because if we don't do that, then we are going to have laws passed that we really don't like, that will look very innocent, but will end up in us being at a significant disadvantage versus the mountain of data that we don't have access to, but that describes us. You could very easily take an example of an insurer who would want to know everything about you, then extrapolate from that when you're going to be sick, with what you're going to be sick, and then they will give you a rate that you cannot escape to pay your monthly premium for insurance, right? And in some countries, this is already happening. So we don't want that to happen. Maybe in 50 years, somebody would call me old school or old-fashioned or something like that. But I would think that, the social contract we have in Europe doesn't go in that direction, right? We don't have necessarily that philosophy. There's also, of course, the option to do nothing, but I didn't put it on the slide. And then another option is to, counter technology with more technology. But this is more or less what we're doing right now, and this is a never-ending arms race. Even for, a very qualified expert or nerd in privacy, it is very difficult to say, these are the actions I'm going to take that maximize my privacy, and I'm going to keep doing that for the next year. Because things will change the next month, right? Things will change very quickly, and they will change a lot. And this is very risky. So I would say that, none of these options is sufficient on its own, and we should have a mix of those with an accent on regulation and definitely an accent on technology that allows us to prove that certain things happen or don't happen, right? So it's a way of enforcing transparency, but it's also a way of enforcing an understanding of who knows what, right, and under what conditions. This defense can be technical, it can be legal, it can be societal. Hava Siegelman from DARPA says that in a very real way, we've rushed ahead, paying little attention to vulnerabilities inherent in machine learning platforms, particularly in terms of altering, corrupting, or deceiving these systems. And she speaks about this from a perspective of security, right? What they're concerned about is the security of artificial intelligence systems, but that concern about security also tells us what are the weaknesses of those systems, right? So in a way, we're almost becoming the adversary, right, or the attacker, trying to understand how can I fool an artificial intelligence system if I may need to, right? So you can fool AI. You had stories of machine learning put in cars, and then the car is driving on the street and it sees a stop sign, but because there's a sticker or whatever on the stop sign, it thinks it's a 45 mile per hour speed limit, and it accelerates, right? It just goes faster. these kind of mistakes happen all the time, right? You cannot always predict that. So if you put a car that is self-driving on the street, it's a very tough problem, first of all, and nobody has achieved it to a good degree today, despite of all the advertising you may hear. And it can happen because it's an edge case that may not be, foreseen. The sticker, is placed maybe 3 degrees too much rotated to the left from, what the training model might have seen. And then it says, no, it's much closer to a 45 mile per hour limit. So I'm just going to go, right? And then we go and there's an accident, which is very unfortunate. So, you can do a lot of stuff. You can add a bit of noise, for example, to the things that the classifier might be recognizing. And then AI will misclassify objects, for example, as a human when it's not a human. You can play with edges of things. Then AI will say, well, probably that's something different. There are papers even describing a single pixel that can wreck a whole deep neural network, right? You put a single pixel in the right place and the network just goes, I don't know what that is anymore, or this is something completely different. So you see there is a certain sensitivity to unexpected elements, and these edge cases are always a problem. If you cut off too much of them to preserve the privacy of the learning set, which is something we would normally want to favor, then the learning set is not going to be good enough to predict those edge cases in the future, right? So it's a conundrum and almost a paradox. Then there was another interesting case where Microsoft made a robot, a chatbot called Tay, and it basically put it out on the internet and said, hey, people, talk to our robot. It's going to learn from what you're saying to it, and it's going to respond and will become smarter and so on. In 24 hours, the robot turned into a fascist. So that's how long it took the internet to convert the robot, not necessarily, on purpose, but simply, by pumping whatever garbage you could imagine into the robot, and it was accepting everything happily. And it didn't have a value, compass of any kind, or it was not told. Well, maybe you should not say, messages that in other places would put you in court for spreading, Nazi propaganda or something like that, right? So again, that chatbot was defenseless against the inputs that were coming in. There's even another type of attack, which is a model extraction. So you can feed garbage into the model, and then you can see what it produces as a result. And that way you can learn about certain parameters of that model that maybe your model, competitive model, does not have, and you can extract some of the knowledge that is embedded in another model or what data was used to create the training set. Lots of attacks possible. I'll show you just a few examples. It doesn't always have to be extremely complicated. This is an example from OpenAI. We have an Apple at the top, and here we have an iPod. Obviously, the algorithm classifies the iPod correctly, so no problems here, right? We can move along. So there's a very interesting blog post from OpenAI on this topic and how they get around these kind of problems. Then, what do you see? Turtles or assault rifles? More research done. This is from MIT in 2017. You could fool neural networks pretty easily with 3D printed objects. So they would give a texture to the turtle that basically makes the algorithm say that this is a rifle. And you see that out of all these turtles, I mean, as a human, I believe them to be turtles. I don't know if you see something different. Please correct me. But to me, these are turtles. And as you can see, 8 out of 10 are classified as a rifle. Right? None of them are classified as a turtle. So if you can do that, then maybe you can make a bomb and say, put something on it that doesn't make it look like a bomb anymore. And you put it in a 3D scanner at the airport, and the scanner is going to say, you know what? That's just a teddy bear or whatever else, right? So again, I'm not saying we should do that. What I'm saying is there are many ways to fool AI, and that's going to play around with our privacy a lot. What we can do also in an adversarial type of relationship is we can fool face recognition. So there was this project in 2010 or 12, 2010 maybe, created by the artist Adam Harvey, who basically wanted to dazzle computer vision. He wanted to completely fool computer vision just by putting makeup on a regular human face so that the AI cannot say it's a human face anymore. There's a bunch of sketches that relate to this concept. So basically different types of patterns that you could put on the face. And there are even walks. There are whole groups of people who do walks really physically painting their face and then trying to see if the face recognition cameras, first of all, will recognize them as humans, and secondly, whether they will recognize them as those citizens. So this is the so-called Dazzle Club, which is active in London. They were especially active before the pandemic and during the pandemic, and they would, for example, in a provocative way, they would go to whole privatized areas of London. So you probably know that in London there are big areas of the city that are privatized or considered private properties. So there are different rules on who can enter and who cannot. So they would go there and kind of provoke the algorithms, provoke the security, and see what happens, right, with that. So they don't agree with the regulations that prevent them from going there. There was also a story actually related to those areas. There was actually a worker who supposedly forgot to pay for something in a self-checkout. They were caught, and then they were treated like a criminal. Well, they didn't pay for the item that they took out, therefore they are a shoplifter. Therefore, they are banned from the whole estate. Therefore, they cannot go to work because the camera is going to immediately recognize them and security will stop the guy even before he reaches the office. So after a lot of deliberation and after a lot of negotiation, they allowed the person to go to the office and back, but nowhere else. So if he's seen, for example, getting a coffee on the side, sorry, that's not allowed, right? Because they would be considered a shoplifter, therefore a criminal. We don't want any criminals here on this land, and that person has a problem. So that was a £2 item, I think, so in the order of, €2 or €2.20 value. That's what can get you banned automatically from the place. So another technique to, now we're getting into the more computational stuff. Another technique to defend ourselves against these type of things is to play a little bit with the data, right? So make us less identifiable in the data as the system is learning. One of these techniques is called differential privacy. So basically the idea is that you perform your training and your computation in such a way that if you remove one subject from the training set, then the difference between those outputs that are produced in the that are produced by the training are at most epsilon. So basically you constrain to some limited value the potential difference you can have if you remove someone. So the point is to kind of homogenize as much as possible those inputs and avoid statistics that are quote unquote too accurate, right? You want to avoid that. So you protect the data before it enters the model. You kind of introduce noise in the answers, and you should always be able to remove one of the samples to keep the answer that the model gives you as unchanged as possible. The benefit is that you don't compromise the privacy of a person in a large group, but the drawback is that you need a large data set, right? It's only is going to work on a large data set, and otherwise it is a little bit difficult to do. So basically, the way it's normally done is that there is noise introduced before the data enters the model, and some data is randomized through the addition of noise to produce a fake answer. So that means that we can never be sure that that specific piece of data contributed that answer. So there's a lot of work going on around this. If you want to know more, then you should look up the publications of Cynthia work. There are very good talks on there are very good talks on YouTube. Just in 20 minutes, they explain this very, very clearly. So how does this work? Well, let's say we are running a survey at CERN, and we're asking, do you like bosons? Yes or no? Obviously, you work at CERN. Saying no publicly probably is going to get you in trouble with your colleagues. If somebody doesn't like bosons, we're going to have a problem with them, right? So we have a bunch of real answers. And, some people said, yeah, we like bosons. Some people said, no, bosons are boring. We don't like them. So differential privacy is going to pick those answers up, and then it's going to spin this little arrow around and see where it ends up, a little bit like the Wheel of Fortune. If the arrow ends up on the white zone, which we define as we need to statistically, like it happened, for example, in this case, then we change that answer. So we're going to basically flip that answer to something different. And you see that you get a noisy answer out of this through, randomly and in a statistical way, changing those answers. And then when we sum that data up, we are going, well, this is just 5. Again, it's not a big data set, but it's to illustrate the example. When we sum all that up and reduce it, then we will see that we have a distribution that's very close to the original one, but we've protected the privacy of those who are in the model in some way. So differential privacy is very big in machine learning. There are many sophisticated, much more sophisticated methods to train neural networks, deep neural networks, using differential privacy. But they are challenging because if something is fair, if something is differentially private to some extent, then the output may not be fair. You may be cutting out some cases that you normally don't want to cut out, and so on and so on. So generally speaking, it's still a topic of a lot of research, and it is applied in practice in models that are being trained on very big computers, with hundreds of GPUs. But still more work is needed before this is, a very efficient and kind of good enough technique. Then there's another type of, let's say, protection, I would say, so-called data trust. So a data trust is an entity that acts as a trusted data steward on behalf of the parties. So, someone might not trust Google, but they are going to trust DuckDuckGo, right? And then in a way, DuckDuckGo is kind of, absorbing a lot of data, and, in that way, it becomes a trusted third party. So a trusted third party could become a data trust, which means that it would manage the data on behalf of someone else. Now, for me, the concept of a trusted third party is very challenging to accept. In the 21st century, when we have a lot of cryptographic techniques, putting an extra party who has all your stuff sounds a little bit challenging. So I think it's a little bit of a difficult idea to accept. And we will talk a little bit about identity towards the end of the talk, and that will help you understand, how we could avoid these kind of cases. So there are data trusts. So, for example, Open Corporates is a data trust. The UK Biobank is a data trust. Tim Berners-Lee, who we've mentioned yesterday again, the inventor of the World Wide Web, also has done some work on data trusts, right? And on his ODI page, you can find references to that. Yet another technique is selective disclosure. So let's say we want to be able to share cryptographically signed messages, so messages that are proven to be true and authentic by some other authority, but not the entirety of that message. So that's called selective disclosure. And normally what you would do is you would have a message, you combine it with a private key of the issuer, and then that ends up being the signature, right? So that's signed, and that is proving that the message is okay, that the signer has seen it and believes that it is genuine. Well, then they could also take a bunch of messages split up into pieces, so basically parts of the message, again, add their private key on top, and then you get the signature out of it. Well, this can be used in multi-message schemes where you are saying, well, what I'm going to do is actually I have that message and I have the signature that was signed by the issuer, but I want to block a certain part from being seen, and I want to share it further. So what I'm going to do is I'm going to take that, I'm going to combine it with the public key, with the signature, I'm going to produce a proof, right, of that message. And then when the verifier wants to verify it, they get the message with something blinded out. So that part we say, for example, I don't want to reveal my date of birth. It's okay if you have my name and address because you need to deliver the package to me, but my date of birth issued by my national authority is none of your business, right? It doesn't matter if I'm 20 or 27 to deliver that package. And in the same way, they would take the public key, they would take the proof that we've provided, and they would end up with a verification. So this is a very, very simplistic model of how this really works, but it shows to you that you can have messages which are composed of pieces, and then through cryptographic techniques, you can blind out some of these pieces and then selectively disclose only the parts that you care about. And then the verifier or the entity with whom you're sharing the data is only able to see the messages or the credential claims which you have selectively disclosed to them, right? They would not be able to see anything else, and they are still able to selectively verify those claims. So different providers or different technologies handle this in different ways. In some places they would use zero-knowledge proofs. In some places they would use other cryptographic techniques. Nevertheless, that is widely researched right now and is becoming a part of the future of identity and future of the claims exchange that we are building. Then zero-knowledge proofs. So zero-knowledge proofs are a very attractive concept because they allow you to prove something without actually revealing that thing, right? So if in my pocket I have a red ball, I would be able to prove to you that I have it without you ever seeing the red ball, right? And without you knowing anything specific about it, except for the fact that I actually have it. So there's many, many different techniques how to do that. These ideas already came out in the 80s from MIT. And the scheme is always the same. The prover issues a statement to the verifier and then convinces the verifier that they know some mathematical statement, for example, a solution to a discrete log problem or the result of an equation, and they can't cheat, right? So the prover can't cheat because doing that mathematically would be extremely complex. And then they don't leak even a single bit of information about the information that is, about the data that is stored there. So there are three main properties about these proofs. The first is that they need to be complete. So a prover must be able to convince a verifier if the statement is true. Then they have to be sound. So this means that the prover cannot convince a verifier if the statement is false. And then the third thing is that they have to be zero knowledge. So the verifier doesn't get any extra knowledge from executing the proof and so on. So the idea is very simple, but it requires a lot of complexity. It usually requires a lot of compute power, and especially for the interactive types of proof, there needs to be a lot of back and forth. Many interactions are needed. And for many types of zero-knowledge proof, there is not the 100% guarantee, mathematically speaking, that they are going to work, that they are actually correct proofs. It's 99.99999%. You know about that very well from the discovery of the Higgs boson. But it's not mathematically 100%. But for practical usage, this is usually more than enough, right? So there's a very, very tiny chance that you would be able to fool that. And then there's also non-interactive proofs, so you can present a blob of data, and then based on that data, the verifier can actually understand that you're proving something in a zero-knowledge friendly way. So there's a lot of applications of zero-knowledge proofs in crypto, for example. So if I want to sell, I don't know, a Bitcoin to Sebastian, who's in the front row, he's going to tell me, well, prove to me that you actually have it. If I give him my key proving that I control the Bitcoin, well, he's going to have the key and he's probably going to take it away from me. If I prove that I have the key without actually revealing it, then Sebastian is going to be satisfied. He's going to say, well, I trust you that you have the key, therefore please transfer it to me, in exchange for some payment, right? And we can have the transaction. So that's how it happens very often in many types of cryptos and so on. There's also applications in identity. We'll look at it in a moment. The cool thing is that if you combine these proofs or these techniques, you can perform computation. So it's not that a proof is, very straightforward, one thing that you prove and that's it, it's done. You can actually perform combinations which enable you to do very cool things, such as, for example, knowledge proofs. So you can say, okay, does the prover really know the secret? That's the basic thing. You can prove a set membership. You can ask, for example, is the person a paying subscriber? Or is the person's data, who's a presidential candidate, by the way, in a DNA database of offenders, of registered offenders, and so on, right? So you can prove participation in a membership without, revealing too much. You can also have range proofs. So for instance, you can ask, is the person over 18? Is the person aged between 35 and 45? And so on and so on. So there's a lot that you can do with this that leads you to a very interesting landscape where you can do many things without revealing stuff that you otherwise would have to reveal. So how does this work? Let's have a simple example first, which is equality. So let's say there's Alice and Bob, and they want to compare their salaries. So for example, Bob is going to look at a number of boxes that basically represent their salary ranges that are possible. So maybe they make 30,000 a year, 40,000, 50, 60, 70, or 80. And then each of these boxes is locked, Neither of them can access the box, neither Alice nor Bob. And Bob is going to pick one of the keys which corresponds to the salary that Bob has. So let's say Bob makes 50K a year. He's going to pick up this key, and then Bob leaves and goes somewhere else. And then Alice is going to come, and in each of the boxes, she will insert a card that represents whether she makes that salary or not. So for example, she doesn't make 30K, she doesn't make 40, she actually makes 60. So in the 60K box, there's a piece of paper that denotes that, right? There's a circle instead of an X. And otherwise, she doesn't know which key was chosen by Bob earlier. And then when Bob picks up the box and Alice comes back, they open the box together. They see, well, they don't open the box together. I roll back. Bob opens the box. He picks up the piece of paper. And then the piece of paper is the X, right? So then through that piece of paper, they know, no, our salaries are not the same. Of course, they have to collaborate on that. If they're colluding, there's a lot of attacks that you can play with. But this piece of information is the one that they were looking for. Ultimately, if they want to test equality together, then they agree that this is going to be the representation of that equality, right? And then this means, no, our salaries are not equal. So this is how a zero-knowledge proof works on equality tests. And then there are also examples of inequality tests. So this is a very straightforward, very simple example of how this would work. This is only one of many schemes that exist. And mathematically, I think it is straightforward enough that we can chew through it in these discussions. So you have an issuer of a credential, you have a holder of a credential, and a verifier. The issuer, for example, could be a government that is going to determine somebody's date of birth and say, yep, in the national registry, we know that this person was born on this date, 1985, right? Let's say. Then a holder is, for example, Alice, who wants to prove to the verifier that she's over 18, but she doesn't want to reveal her date of birth. She doesn't want to reveal the exact day nor the exact year. She just wants to be able to prove that she is over 18. So what's going to happen is the issuer, which is, for example, the government, is going to take a seed, and that is going to hash it. It's going to make a kind of starter. And then it's going to say, okay, I support this scheme until the year 2100, for example, right? That's the maximum year until which we support it. Then we subtract the date of birth of the subject, we get a value. And then we iterate another hash function many times, to be precise, 115 times, over the starter to produce a signature out of that, right? So we hash 115 times over the starter data, and we produce a chain, so to speak, of these hashes. And then we transmit, just the signature and the starter to the holder. So the holder knows the starter, which is a secret variable, and it shouldn't be revealed to the verifier. And the holder is going to compute a part of that hash that basically corresponds to them achieving the age of 18, which is the test that is defined there, right? So the verifier says, well, prove you're 18. Okay, I will prove that I'm 18. I'm going to iterate n times, which is relevant to the 18 limit that was set. And I'm going to send this proof further on to the verifier. And then the verifier is going to say, well, okay, I got some cryptographic jumble. I have the hash function I'm supposed to apply here. And then I'm going to hash it the number of times that is needed in order to reach the value that is in the signature, in the original signature, which is the limit of the scheme, right? So they hash collaboratively. First, the holder, who is Alice, hashes it to prove that she's 18, right? That she could hash it at least a certain number of times. And then the verifier is going to finish, cycling and repeating over that hash in order to produce something that matches the final signature. And through this, we've proven, without knowing that Alice is 18, that actually Alice is over 18, right? Then there's other schemes that go more towards machine learning. So for example, multi-party computation, and this allows mutually distrusting parties to cooperatively compute over their private data. So theoretically, it can be pretty much any function. So you can split up the data into pieces, send it to participants for computation, compute it, and then reduce the partial results. But because you've split it up, nobody really knows what the data is. So there's no trusted party in the middle. You don't need to reveal a single bit of private data to another. And the compute cost is negligible. There's a high communication cost, but the compute cost is very low. So you could imagine, for example, if we're in a group and we want to calculate our average salary without revealing those salaries, then there's a mathematical scheme that allows us to do that. And this is also used a lot in, for example, crypto exchanges to release funds. You could have shares of keys. For example, a share of a key, a private key on a smart card, another share on a computer in a security module, and yet another somewhere else. And together you could compute the whole key without actually revealing the little bits and pieces, right, that are sitting inside. So all this can be very useful. You could also imagine, for example, internet service providers who, where the government wants to search network traffic, but the ISPs don't want to reveal what exactly their customers are looking for, right? And they don't want to reveal the traffic either. So there's a lot of caveats. There's a lot of cryptography here, a lot of inefficiencies as well, but this is the general model. This is how it works. So let's say we're doing exactly that. We have 4 persons who want to check their average salary without revealing the salaries. So you have person A with salary A, person 2 with salary B, C, and D. Then you are going to distribute, you're going to split up this salary, and you're going to send little bits and pieces to different parties that take part in the computation. And then the same happens for all the other salaries that are composed of little bits. And then what happens is each party sums the bits that they got, so they don't know how much the others have sent them, and they don't know the values. They could be even negative. So, just because someone sends you a value X does not mean that's, anything to do with the salary. It just has to sum up at the end of the day to the salary. So all of them compute privately their sums, and then publicly the results of those sums are shared together, and you can get the salary out of that, right? So again, very, very roughly, this is how multi-party computation works, and then you can make it much more complex to put it in a cryptographic scheme, and then you do very fancy stuff with that. Then yet another very interesting and relatively recent development is so-called homomorphic encryption, or fully homomorphic encryption. We're going to focus on that one. There, the idea is that you compute on entirely encrypted data. So, for example, if we put a 9 here and a 6, we're going to encrypt it with a key that the let's say requester has. You send complete gibberish, or at least that's what it looks like, to a cloud computer. The cloud computer, that the cloud doesn't exist, right? It's just somebody's computer. You basically add those gibberish pieces with a special algorithm. You send back the answer, and then the same key is applied to decrypt it, and you get the answer there. So it's homomorphic because there's a structure that preserves a map between 2 algebraic structures at the same time, and you can perform binary operations on the data without ever decrypting that. It is orders of magnitude slower than multi-party computation for most use cases. Even 5-7 years ago, this was something almost impractical to have, almost impractical to execute. Today, it has gotten much faster, so it's still 1,000 to 1,000,000 times slower than unencrypted data, but it's picking up in speed, it's picking up in efficiency, and computers are getting also more powerful. And in 2015, they managed to compare 2 pieces of DNA using this algorithm in less than an hour. But 4 years before that, to compute just 1 bit of information would take 30 minutes. So you see that there was a lot of progress in that respect. There are also approximate schemes in homomorphic computing. So you could say, if I do machine learning, I don't really care, if it's 100% something or 99.7% something, and therefore you could apply this kind of operation. So you can do addition and multiplication relatively in a straightforward way through homomorphic encryption. Scalars, vectors, matrices, and so on. You can do polynomials. Testing for equality is possible but hard, so there are tricks around that. Comparison is very difficult. So a famous example is how do you compare -1 and 1 modulo 5, right? It becomes a very difficult challenge. Or how do you compare 0.999999 and 1. Then you can do some approximations of nonlinear functions through polynomial approximation. So lots of research ahead, but I wanted to tell you that you can have fully encrypted data, and there's a way to compute on it and produce a result without ever knowing what is in the data. There is also searchable encryption, which can be based on secret keys or public key cryptography. The idea is that basically, again, this is one of the simplest schemes. There are many schemes, I don't know, 20 at least, but this is the simplest scheme. You would encrypt a document with your key, and then you want to be able to search through it. So you're going to say, okay, these are the keywords I'm going to search for. You kind of predefine them, and you hash them. So I hash CERN, I hash secret, I hash lemons, and then I send all that to a cloud provider who has no idea what I just sent, right? These are just bits and bytes. Unless they know my key, which they never should, they will not know what is in there, and they don't know what I'm looking for, right? So when I'm looking for a secret, then I send the hash of that secret to the cloud. The cloud is going to find it somewhere and say, this document contains it. Therefore, back you go. This is your document. So then there's lots of advanced schemes to search for ranges and so on. And then we have so-called federated machine learning. So you can see probably already, the bricks are falling into place in your mind that a lot of these concepts can be applied to machine learning, where, for example, central servers have some kind of model to be trained, and then they transmit this initial model to many nodes. These nodes train the model locally with their data, and then they send back, not the data, but they send back parameters of the model. And then the server will pick that up, is going to say, okay, you sent me this, you sent me that, and this other device sent me yet something different. And for that reason, I'm going to make an iteration of the machine learning algorithm locally on the server and send it back to the remote clients, right? The parameters that I have. So iteratively over time, they can learn without knowing what is the data inside. But from a privacy standpoint, again, there are the usual questions. What if the model remembers something, right? What if the model memorized some of the data that I put in it, right? Would it reveal some kind of statistical significance of the things that are stored on the client? This is always tricky, right? So you have to be cautious about that. And then again, there's a lot of research in federated distributed machine learning where you can do a lot of work without a central server, but you have to be careful about how you treat the data. You may need to add certain regularization terms to your machine learning, and so on and so on. So there's many optimizations that can be applied to it. So to move on to the kind of last part of the talk, let's try to kind of come down to earth. Again, this is AI generating a picture of the earth with powerful AI on it. That's what it sees the earth like. So a cool science fiction-like picture. In practical life, what does this mean for us? I think there's 2 or 3 main applications that are very worth discussing. Your interaction with the government, that encompasses identity and that encompasses money. And then our interaction with automated systems. So basically decision-taking, profiling, and so on. Money and identity privacy, I would say, are definitely pillars of many modern societies. When you spend money, you don't expect anybody to be looking at you, what you're doing, right? When you spend cash, you don't expect somebody to be looking at what you're doing. This is what cash has always had as a promise. Today, we have so-called cashless societies or countries which kind of phase out slowly the usage of cash, but they see over time, like for example, Sweden, that this is a very difficult thing to do because citizens don't always know how to use digital technology, so it's not inclusive to do that. And they don't always want to be followed by digital technology, right? So it doesn't give you a guarantee of privacy. So, are we doomed in that sense? Are we doomed to pieces of paper, that will be always there? And I think that there's some very interesting stories to explore here. So we'll get to that in a moment. So this is related to privacy because you don't want your transactions to be published in the news. You don't want your passport page to be published in the news either, right? This is directly related to privacy. But whether you like it or not, your identity is given to you by a government, right? I cannot say I am Andrzej and then venture wherever. I can only go so far until somebody stops me and they say, well, you need to prove to us that you really are Andrzej. How do you do that? Right? This is the challenging topic. So we want to control our identity. we want to control who knows it, and we want to be anonymous for many reasons. So there's good news. There is a scheme that can help us do that, and it's called decentralized identity or self-sovereign identity. And we've spoken about this also in April, but I wanted to bring it back because it really has a lot to do with this automated data vacuuming and correlation. One of the fundamental tenets of decentralized identity is that there are new pairs of identifier generated for each relationship between issuers and holders. Therefore, just because I hold a Visa card does not mean that I will be correlated to my MasterCard, right? So basically, the issuers will necessarily have my data and will be able to say, yeah, that guy has a card with us, but I will be able to prove to people who ask me for proof that I have these cards to do that in a way which doesn't allow them to correlate this information, which is a very powerful thing to have. So in these schemes, an issuer will sign claims, so-called claims, verifiable claims, will issue them to holders who will also sign them, and then those claims will be presented to verifiers. And then there is a kind of root, or there's a kind of anchor, which can be the blockchain, which can be some other database that stores decentralized identifiers that allow the holders and the verifiers and issuers as well to talk to each other. So they only tell you, how do I contact someone? It's not anything more than that, right? So it doesn't hold your secret information. You can present those claims yourself, but the DID, the centralized identifier, is going to basically tell others how to make a link, in this jumble, in this web. But in the end, you end up with at most a triangle, right? You're not going to make a network. You end up at most a triangle where you have the issuer, verifier, and the holder, and that's it. And they talk to each other, and through these contacts, they can present and prove data and identity without actually the others being able to correlate it. So by combining these technologies, you can do a lot. The second thing that was mentioned, and I think is very important, is the concept of the so-called central bank digital currency. So we've said we have cash, which is physical money that we can hand to each other. And I think that this cash is not going anywhere anytime soon for many reasons. One of its main properties is that it's private, it's anonymous, it makes you anonymous, right? If I go to a store and I purchase, I don't know, let's say a protein drink, for example, I'm going to pay with cash. Unless someone films me doing that, nobody will know I ever bought it there, right? And that's important for many reasons for us. It turns out you can do it in digital ways too. So digital currencies can be designed in a way, using the techniques we've just seen, that is preserving the privacy of citizens. But then you might say, well, what do I do if, criminals start money laundering on an enormous scale, right? So if they become anonymous, it's not good for society. The thing is that there are ways to build rules into cash, into digital cash, right? And central bank digital currency, or CBDC, can be made to respect those rules in a cryptographic way. And we could say, for example, that we can exchange value between each other, even in an anonymous way, and even offline, up to a certain limit, for instance. So if you take, there are countries which limit you to spending 1,000 euros in cash. Mostly this is done for tax evasion purposes. They just want to know that transactions took place. So we could say, okay, if we are spending, for example, under 1,000 euros or under 2,000 euros, then cryptographically it is provable that nobody will ever know that we did that, right? The only thing that's a difference is that the merchant has, the amount of money more, that I have less in my account, and we've exchanged a good, right? That's what happened. So these technologies can also be used against us, but my point is rather optimistic. There are technologies in there, buried in there, that can make us stronger, that can allow us to defend against this. And again, this is a reason why I think we should keep pressure on governments to remind them that privacy is important to us, and that new technologies that are being produced, sometimes by big companies, the interest of which may not align with others and with us, these technologies also should serve us. This is very important. And the people have spoken. Here is a survey from the European Central Bank about the introduction of the digital euro, and they've asked openly the public, this means corporations, small companies, private citizens, and so on, merchants, to tell them, what are the important things you think should be considered when we possibly one day make a digital euro? And it turns out that privacy was at the top. It was the most voted first rank and the most voted overall out of all these topics. Now you will say probably, you're good scientists, you'll probably point out this is a kind of bias, right? In the sense that this survey probably reached those that care about it a lot, and these are the answers that they gave. Fair enough, that may have been the case. Nevertheless, this is the answer. This is the most democratic process we have. We vote on what's important, right? And the vote has happened in the first iteration of this discussion. So even if it doesn't end up being the #1 concern, I'm willing to bet a lot that it's going to end up one of the top concerns. And if we speak of digital cash, most people will want to think about physical cash, the properties and attributes it has, and how to transport that onto the digital domain where it gives us the same level of convenience. So our privacy can be protected. So lots of these technologies, zero-knowledge proofs, anonymous protocols, even blockchain-derived techniques can provide a lot of value here. It doesn't mean that the blockchain must exist in currency or that it has to be based on a blockchain, but I would say that the development around cryptocurrencies and blockchains enabled us to push cryptography also further. So it was as much benefiting from these developments as generating them. So the last topic, automated decision-making. Automated decision-making doesn't necessarily have to include profiling. So these decisions can be taken purely on the basis of some parameters that are available at a given time. The things we have to ask about are, what is the decision object? It could, for example, be a loan application. It could be an online recruitment test. It could be something else. What is the model or the rationale for this decision? What is the data coming for that decision? What is the quality of the data in that decision? Let's say I'm applying for a job and I fill in a recruitment test, but then the program was not written in a very good way, and then it maybe fuzzes 2 or 3 of the answers, and then it ends up showing some kind of different answer from the one I gave. The robot then says, this guy is not very smart. You shouldn't take him. The recruiter who has to read 10 CVs an hour or 20 CVs an hour is not even close to contesting that judgment, right? They will say, no problem, there's 50 others who passed the test. Therefore, it doesn't matter anymore, right? So if a judge listens to this software that tells them how likely a person is to reoffend, is this decision automated? Is this decision not automated? It's something in between, right? There is a human in the loop, but they are very likely going to be subject to automation bias, right? We accept what the computer says. So, there are many risks. This kind of decision-making is often not visible and transparent to individuals. People might not expect their information to be used in this way. People might not understand how this process works and be against it. And then the decisions taken could lead to significant adverse effects for people. So there are national laws that say in many countries, or even in many states of the US, that say if a decision has a legal-like effect, then it cannot be truly automated, right? Or it cannot be fully automated. The subject must know about it and must be able to have a recourse. So I think this is a real risk to human agency, because robots will take decisions which on average might be good, but then there are bugs. And we don't know today who is supposed to be responsible for them. Who is going to fix it is the question we asked yesterday. And unfortunately, the answer is not there. The thing is that these automated decisions can kill you, and there's proof for that. You might have heard about the Australian robo-debt scandal. So basically in 2016, the Australian government started issuing automatically debt notices to those who were receiving certain type of welfare. And then this program automatically compared the income that was declared to the Australian Taxation Office against the income declared to the welfare program. And then if there's an issue, this would result in debt notices, and then there would be a 10% recovery fee, whenever disparity in this government data was detected. But the problem was that the calculation of debt was done incorrectly. So basically, it was basing a certain type of average rather than taking a cumulative snapshot of the pay they had. And then this average would be different for most people. So at the end, between 20 and 40% of these debt notices were wrong. 700 million Australian dollars. It's an enormous amount of money, right? We're not talking peanuts here. We're not talking one random guy losing a job. We are talking about a whole nation criminalized automatically by a robot. So 500,000 debt notices, almost 500,000 debt notices were wrong. And then some of the people who are in this scheme, more than 3,000 people, actually died before this scheme was rolled back several years later. So there was 5 years, I think, of fighting before the government finally accepted that it made a mistake. And this resulted in several suicides. So very unfortunately, that decision made by a robot that was written in a clumsy way and, didn't take into account everything by the government that, it's a basic thing you think about it. But then, okay, there has been, a space shuttle disaster also from something that seems very simple, right? Confusing units. In a complex system, these things can happen. It doesn't mean that the people involved in this have bad will, but it means that we are definitely exposed, and we don't always have, as humans, the capacity to teach the computer everything we need to teach it. So in a way, it is human arrogance to think that we can do better than that, right? And this arrogance can end up in death, which is very sad and unfortunate. The lawsuit, by the way, is double the amount, 1.2 billion. So now you see. In the end, the taxpayer will pay, no problem, right? So there can be recourse against automated decision-making. In the GDPR, there's an article for that, which basically says that, it has been watered down a little bit, but it basically says that if there are legal effects producing or similarly significant effects producing from that decision, then the individual has a right to not be subject to that decision, which means you have to redo the whole decision from scratch very possibly. And this has been confirmed already in Denmark by the Danish authorities, which ruled that the controller must answer clearly if automated decision-making takes place in the context of an access request. So that has already been kind of tested, right, and is out there. And then there is something that is, almost more troubling, which is automated profiling. So it's also in the GDPR, the General Data Protection Regulation, which says that profiling is any form of automated processing of personal data consisting of the use of personal data to evaluate certain personal aspects that relate to a natural person. So analyze and predict aspects of that person's performance at work, economic situation, health, and so on and so on. So profiling can go quite deep. You can have relatively innocent profiling, such as the advertising profile. From the example from yesterday of pregnant women who are profiled and then advertise products to, you see that it's not that innocent, but that's the least innocent type of profiling I think we can consider. And then you can try to establish a certain person's level of influence. I'm sure that Instagram checks who is a real influencer and who is just playing one. And then those get different kinds of treatment, right, and are valuable to advertisers. Recruitment, is that person a good candidate or not? Have they been a good candidate for the last 5 years? I apply today, but what kind of person have I been 5 years ago or during the last 5 years? My profile is on LinkedIn. Maybe I've edited it, and maybe I've put in things that I haven't really done, and they can detect it, right? So again, this kind of stuff kind of builds on the rich fire hose of data that is everywhere. Then there's dominant emotional states. You could analyze weaknesses of a certain person. If, for example, you go to work, every time you pass a camera on your way to work, that camera knows if you're happy or not, right? It's going to know sooner or later. Probability of disease, reoffense profile, and so on. So, the creepiness is already pretty high when you start here at the top, but it only intensifies as we go deeper. So, this can be used for good. This can be used, for example, for medical treatments, finding out, collectively, the intelligence of our bodies can help us make better drugs. I deeply believe that we can do this and we should do this, but we should do it in a way which is respectful of privacy and which doesn't push us, into a complete lack of control. Profiling leads to bias, right? And profiling is inherently infested with bias. And these biases can come from many different places. I don't speak about it a lot because Stephanie already covered this yesterday, but the main types are the human bias. So basically, as humans, we are fallible, we have to accept it, and therefore we pump the system with data that also might not be very good. There is a data sampling bias, so the data fed into the system can have a sampling bias, and then this has been, for example, the case where, there were AIs that declared that a man is to a doctor what a woman is to a nurse, right? That is a sexist statement, but the AI produced it because this is what it saw in the biased data that it was fed. Long tail biases, again, there are issues with whatever sits in the long tail. Certain categories can miss from training data. There's intentional biases, so nefarious actors can inject data into your AI and make it take decisions that are not in your favor. Imagine that there's a company that wants to trip up your company, right? You're the CEO of a company and they want to make you lose money. You're competing very hard. They will feed your AI with something that's going to make you take decisions only 3% worse. But if it results in a 3% lowered margin, well, you could be out of the market, right, for some reason. So there are very small things that could generate a big outcome, right? And then there's hidden biases, so there could be unintentional bias in AI that's never discovered. So I'm not entirely in the camp, of defeatists who would say, well, AI is hopeless, there will always be biased, AI is racist, and so on. I don't believe that. I believe that we have to be very careful and we have to do a very good job in making sure we feed the AI correctly, we control it correctly. But how can we control it, right? This is the tricky part, because putting proper quote-unquote data is maybe possible, but we don't really know what's inside, right? So how do we explain AI? I asked the AI to explain itself, and this is what it made. This is the picture I got. Somehow I get, all these cool-looking, modern paintings from the AI. It's also from Stable Diffusion. Okay, jokes aside, how can we explain AI? This is a very big issue, right? A big topic of conversation right now. We want to explain it because we don't know what the thing is doing. And we, on one side, may want to interpret the AI to know why this decision was emitted. But explaining it is something more. It's a little bit more. It is understanding how did we get to this result? Not why, but how. What was the process? What was the sequence of steps? How did we understand in which way that we are at this decision, right? So from a privacy perspective, it is, of course, useful to know if the AI will reveal our data. But we know at the same time that the AI has been memorizing some of our data, right? It can happen in training of deep neural networks if we don't take sufficient care that it would memorize some of these things. So then if someone wants to find it out, maybe they manufacture a query and they can know something. There were cases where, for example, research groups from very esteemed universities have done research, and then they themselves have found that, as they started to explain what happened, they realized that the results were very biased. For example, there was an AI that was supposed to analyze the scans of patients, the medical scans of patients, and then say if the patient is sick with something or not. So the AI was kind of okay, but not very good. It turned out that the AI, as a main parameter, would take the fact whether the person was laying or standing while being scanned. And that was a very important thing, because when they lay, they are already sick, right? And they are scanned by the machine. When they stand, it means they are probably okay, and it's less likely something's wrong with them. So you see, stuff like this is very straightforward, but if we cannot explain it, we cannot catch it. So to explain AI, we need to be able to interpret it, and that's already quite a challenge. The best labs, IBM, Google, others, they are working right now on these kind of topics. There are many methods to do that, but they are still young. And at the end of the day, we will have to do more research and more work, right? We might be able, for example, to get predictions about how much a certain factor will affect the final result. There's some kind of traceability, a decision explainability built into the models, but ultimately it's difficult. So here I just wanted to put an example from a person, publishing a blog on Coder's Kitchen. And this is a so-called saliency map of a picture, which on the right-hand side shows you why the AI thinks that it sees a lion, right? What were the features or what were the little bits and pieces that it took into account that the AI used to make it think that it was a lion? So in some cases, machine learning could be explained easily by, for example, using rather transparent models, such as decision trees or Bayesian models, rule-based approaches, even, k-nearest neighbors, things like that. But for more advanced models, or especially neural networks, it is difficult to visualize them. And even if you do, you don't know what's happening, right? You don't know on which layer of the neural network the decision was taken. So you might be able to understand some things, for example, which neurons are firing when you work and when the neural network takes a decision, and generate maps like these. But sometimes it is quite difficult. So in computer vision, it's a little bit more straightforward. But there's other work going on, for example, in natural language processing and elsewhere, that aims to explain a little bit more what the model is doing. And in some cases, especially when you do medical type of processing, this is extremely important, right? You don't want the model to kind of do things in the shadows and you don't know what it really is doing. Today, there's even Coursera topics included, courses on these things, so you can learn about that easily. So to conclude, machine learning and your data means that your data lives somewhere in derived formats, right? In statistics, in machine learning models. So if you combine it with the right to be forgotten, what do you get? Well, in fact, it seems that you get machine unlearning, and that really exists. That's a real topic. So what you can see is that if you combine a very hard approach to GDPR with machine learning models, you could have subjects who say, I want my face removed from there right now. What do? Do you retrain your model on 200 GPUs and spend $500,000? Or do you find a way to remove that person's face from the model without retraining the whole thing? So there are ways, this is an optimistic message I want to leave you with towards the end. There are ways for us to continue, this battle for privacy, this battle for the right to be forgotten, and even in very complex models such as machine learning, you can put it in place, right? And that's something that is, at least for me, a very positive development. It will take a lot of work, and it may be algorithmically expensive, but it exists, right, as an option, as an avenue. So I would recommend 3 things. First, I would recommend we always think of data and trust minimization. Focus on those things. We don't need to give a lot of data. The way to avoid a lot of this is to anonymize the data in a smart way. So meaning preferably not give it at all, but if you have to give it out, make it as indistinguishable as possible. Minimize the amount of data we share. Minimize the trust. The second thing would be to focus on open and transparent solutions. I am always in a strong favor of transparency. What is the future of technology in government, I think, is implementing algorithmic transparency, algorithmic laws, so we understand and explain things that can happen, and then we can make them better. And the third thing, do share your knowledge. If you heard something interesting in this talk or in the talk by Stephanie, share it with your colleagues, tell them what you've heard, what you've understood, read a bit more, and take the message forward. So you definitely have a place in all this, you have a role, and the trust that we put in different institutions is always conditional on the interactions we have, and it emerges from the interactions that we have. If you'd like to know more, you can read Weapons of Math Destruction by Cathy O'Neill. Great book, also recommended by Stephanie. Stephanie's book, of course, was discussed on Monday and Tuesday. This is definitely something interesting. She's here because we read the book and we thought, she had a great discourse. And then another book that was recommended to me recently by a colleague is Rebooting AI by Gary Marcus. So there's some very interesting passages in it, and I think it's worth it to take a look at it if you want to learn a little bit more. So I'm leaving the floor open for questions for those who are not starving yet and who still have some time to spend here. And I'm leaving you with a quote from Banksy, who says that invisibility is a superpower. So he's a notoriously hidden artist. And I think this is a quote that we can take with us as we go further in battle for privacy and data and humanity against robots. Thank you very much. It's been a pleasure to be here. Happy to take questions.
Thank you so much, Andrzej, so much. Wow, it's a pity that we couldn't have another day tomorrow. Andrzej was not available tomorrow, but there is so much wealth that could be discussed tomorrow as well. And it's so kind people stay around still. So yesterday we took questions from the room first. How about going back to Zoom today again? There are 2 comments there and 1 question. So I take the question first and then go up to the comments for the people who would like to explain them. And I shall put these links contributed by Andrzej and Stefan on our event page so that people can look at the articles after the chat is out. How would you like Pingyangu to ask your question? By unmuting, or I read it? Would you unmute? Hello. Okay, so I read it. The question is, can metaverse play a big role in massively decentralizing identities?
I think it's a challenging question because I believe we don't understand well what the metaverse is and will become. But I think that the more we transact online and the more connections we have, which is something the metaverse definitely will promote, the more we have a need for a scheme like decentralized identity in order to provide us with a safe way of transacting, with a safe way of proving our identity or our attributes without having to reveal everything to strangers.
Mm-hmm. Thank you. So I don't know if Ping Yang Gu would like to... Oh, she said, fine, thank you. So Andrzej, would you like to summarize the link, or it's enough that we include it in the material and that's it?
Which link, sorry?
Andrei Dumitru has put a link from European Regulation Agency. It's enough, he says. People are shy today. Stefan, would you like to say about today's Wired article?
Hello. No, I haven't read it yet.
Okay.
I just received a notification from Wired while you were talking, and then a few minutes later you mentioned this article.
Okay, so I
will read it.
I have
Thank
put
you.
it in. I'll put it in the material. It's an article that has titled "San Francisco's Killer Robots Threaten the City's Most Vulnerable." And it was about the time that Andrzej was talking about the person being recognized amongst 60,000 other people in a concert.
Yeah, so I haven't seen or read the article, but the story is the one I mentioned. I don't know what is in the article, but obviously, some of it may be just press kind of hyping it up and making it more edgy, let's say. But the problem is there, right? So we have to ask ourselves, if there's a robot, is there someone controlling it, and how does that work, right? Is there a human? Because ethically, we are still used to dealing with humans and not machines. So we still have a lot of work to do before we're probably fully comfortable with these ideas.
Okay, thank you. Would people in the room want to ask, comment? Sebastian.
Hi, Andrzej. Thanks for an excellent talk, as always. So with my security background, I have a question. Fooling AI by, you mentioned this, that someone could, try to fool either by injecting, crafted data, training data, so that the model works not the way it kind of should work, or perhaps then fooling it by injecting the data that is then treated by the model. But this, of course, is much harder than kind of hacking or tricking deterministic systems, right? I can imagine simple cases, but I guess, okay, attacks will only rise in complexity as they did for normal security, but it's hard for me right now to imagine without knowing the model how someone could, try to fool it to their advantage. Not just fool it, however, but to their advantage.
I think it's a very good point, but I also think that you can, for example, if you make a model that's recognizing apples, right, and for some reason this is a very important military application, if you make that model, confuse apples with something else just 5% of the time, right, if you know where they are getting their data and you manage to inject something into it, then you're making that model less efficient at detecting apples. And so, from that perspective, I think these attacks almost must be taking place today. We probably don't know about it, but I would be very surprised if they don't, right? If these kind of injection attacks don't take place. Maybe there are public databases, which are public so that they grow rapidly, that are later used for training, and maybe we can inject things into those databases that allow us to avoid recognizing certain things, right? So I wouldn't be surprised if this is already happening, not with a deterministic result, right? But at a scale that is definitely observable. And that's, I think, the difference, right? Because a deterministic system has a deterministic result. If you hack it in a deterministic way, it's also a deterministic outcome. In this case, we just have to accept that it's a statistical outcome, but we might be, slightly making something better. So my answer to you is, probably we don't get a deterministic outcome of hacking AI, but we are definitely going to get an outcome, and I'm pretty sure this is happening.
Thanks.
No proof, just a hunch.
No, but I share the worry and the feeling, but thanks.
So, anybody else? I see nothing here either, and feeling that everybody may be hungry, I must take a second to say, first, thanks to Andrzej, because his last spring inspiring talks inspired also Gabi to write to me and say, can we have more of that? Thanks to Andrzej for having been the link between me and Stephanie and led to her invitation. And thanks so much to my dear colleagues and security experts, Liviu, Sebastian, Romain, Andrei, Dumitru, people I talked to. And we shall have more of this, as Andrzej also said, early spring. Thank you all for bringing this knowledge, for raising awareness. Thank you so much. It was really wonderful this week. Thank you, Andrzej.
Thank you very much. It was a pleasure. Of course, as you said, it was it was based on many different inputs. So thank you very much to all of you for the invitation. Thank you to CERN, and also to colleagues Stephanie here, Natalie Rauschmeier, who's at Google but was at CERN, Liviu Valsan, who's at CERN, who also consulted for this talk. So thanks a lot for listening, and I hope it was useful.